This year we'll have not only this kind of meetings, but also some personal meetings. And the people from abroad, they may have the possibility to visit us personally. In any case, today, the talk today is by Antoni Rangachev, and this is Evaluation Theorem for Noetherian rings. Please, Tony.
Thank you. It's a real pleasure to speak at the Algebra and Logic seminar of the Institute of Mathematics. So today I will talk about a result that appeared in a paper called Evaluation Theorem for Noetherian rings. So it's the paper bearing the same title. It's an accepted paper in Michigan Math Journal. And some of the techniques were developed in another paper that appeared in the Journal of Pure and Applied Algebra last year. My talk will be in mostly in algebraic language. From time to time, I will refer to algebraic geometry. And I will also mention some connections with complex analysis. So the results can be stated in various ways and can be interpreted in geometric, analytic, or a purely algebraic way. So let me remind you, let's start with some definitions. What is an integral closure? So in my talk, I know that this is a general algebra seminar, and so here I have to really specify that I will be dealing with commutative rings, integral domains. Yeah. So here is a definition. Given an integral domain R, the normalization or the integral closure of R in its field of fraction is denoted by R bar, and it consists of all fractions that satisfy an algebraic equation of this form. Okay, so we say that R is normal or integrally closed if R is equal to its integral closure. Okay, so this is classical integral closures. I think historically first appeared in number theory, in the study of algebraic numbers, but then they appeared later in algebraic geometry, in complex analysis, and other fields. So this is a very, very fundamental notion to mathematics. So let me give an example in geometry. So start with this algebraic variety, an nodal curve. So this is the variety of given by, so this is the hypersurface or curve in the plane given by this equation, the zero locus of this equation. You can assume I work over the complex numbers, and my R here is the coordinate ring. So this is, or well, K is the ground field. Now the question is, what is the integral closure of R in its field of fractions? Or the normalization? Well, one can check that, in the field of fraction, we have this fraction here, y divided by x. And one can check from the defining equation, y squared minus x squared minus x cubed, that we have this relation. Okay, so this is an integral dependence relation, y divided by x squared. So we don't have a degree 1 part, we have a degree 0 part, x minus 1, which is just a function on our, a polynomial function on our original curve. And then it turns out that our bar is R adjoint this fraction. There is only one element here that really matters, which is isomorphic to a polynomial ring in one variable. Geometrically, this corresponds to this singularization of this curve. So you see these two strands that meet at a point. So the normalization separates the strands and you get a smooth curve. So this is an important question. So here, an important example, normalization, the normalization procedure in algebraic geometry resolves the singularities of curves. So let me remind you some connections, more general connections of the normalization to algebraic geometry. So X will be an algebraic variety. You can always assume that feel more comfortable that this is over the complex numbers, over, well, algebraically closed field. What I'm going to study now is this map. So we have this map. So this is the normalization. I'll call this map N. So locally, if you just work, locally, so this corresponds to the spectrum of a ring, Noetherian ring, and this corresponds to the spectrum of this R bar. Okay, so this map, so the properties of N, so what do we have for N? It's finite, it's a finite map, meaning the fibers are finite, and birational. So generically, it's an isomorphism. So now what are the properties of X bar? So as I said, when the dimension of X is 1, this X bar is very nice, it's non-singular. So, but we have other properties as well. So this goes back to Zariski. So it's part of what's called Zariski's main theorem. So if we have a morphism from some other algebraic variety to X bar, which is birational, meaning generically an isomorphism, and the fibers of F are finite, then this X bar is isomorphic to an open set of the normalization. So, or in other words, if F is, well, I mean, this is a consequence of what I just said, but finite, I'm sorry. If F is bijective and birational, if it's just bijective and birational, then X prime is equal to X bar. A very nice property of the normalization. Second property is just if I have a birational map, if F is, so let's forget about this bijectivity or finiteness of the fibers, just the birational map to the so X prime to the normalization to a normal variety X, then the fibers are all connected. This is another form of Zariski's main theorem. As I already said, the normalization resolves singularities of curves, but more generally, what we know is that a normal variety has no codimension one singularities. And because for curves, there can be only codimension one singularities, namely points, the normalization is smooth. Okay. So another interpretation. So as I said, these are interpretations, properties of the normalization in the language of algebraic geometry. Now we can give one which is in the language of complex analysis. How do we describe the normalization? So each meromorphic function on X, which is locally bounded. Here, implicitly, what's assumed is locally bounded at the singular points. But yeah, locally bounded is holomorphic on X bar. So it's kind of a removable singularity theorem. That's what's involved here. You start with a meromorphic function. It does not assume it does not blow up locally at a point. Then on the normalization, that meromorphic function becomes holomorphic. This is something that my colleagues from the Department of Complex Analysis, I think, will appreciate. But the real question now is, which leads to the main result of this talk, is how do we get the normalization of a Noetherian domain, integral domain, algebraically? Okay. So the normalization is this nice object that we want to get equations for it. We want to be able to compute it and deal with it algebraically. So a classical result due to Krull, I think this is from the mid-30s, last century, is that the normalization or the integral closure is the intersection of all valuation. So where V runs over all valuation rings in the field of fraction that contain R. So what is a valuation ring? So let me give you a brief definition. So these are kind of the nice, besides fields, these are the nicest rings that you can have. The structure of these rings is fairly simple. So V is a valuation ring if for each fraction X, either X or X inverse is in B. Okay, so this is not a very descriptive definition. I will give a descriptive definition of a special class of valuation rings called discrete valuation rings in a second. So there is a more precise version of Krull's result, supposing that, assuming that the normalization is Noetherian. Then one can take one can restrict this intersection to a special class of valuation rings called discrete valuation rings. Discrete valuation rings. I will denote it. Denote it in this way. And furthermore, these V's have a special form. These V's are the localization of R bar at height 1 primes. Okay, so you localize R bar at a height 1 prime, you get a discrete valuation ring. What is a discrete valuation ring? Well, these have a very nice description. I will remind you of it. So a discrete valuation ring, a DVR. Well, I need to start with defining what a valuation is. And then I'll define what a discrete valuation ring is. So discrete valuation on the field of fractions, it's a function from the field of fraction minus 0 to z. These are the integers, such that for all x, y, field of fraction minus 0, we have the following two properties. The function of the product is equal to the sum of, so v of xy is equal to v of x plus v of y. Second, we have the inequality. V of x plus y is at least the minimum of v of x, v of y. So here I assume x is different than minus y. And then a DVR, a discrete valuation ring, is the ring that of all fractions with a positive valuation. So this is, I mean, I apologize to all of you who are familiar with this very basic concept. I think it's good to review them. So let me give you an example. So you consider Z localized at a prime ideal P, that this is all integers divisible by a prime number P. So these are all fractions, Z divided by N. So Z and N are integers, such that P does not divide N. So this is a discrete valuation. So you see what is the valuation? Then the valuation is simply, so the valuation associated with it is the order function. So this is the maximal power of P that divides Z minus the maximal power of P that divides N. And so all elements with a positive valuation, with a non-negative valuation, so they correspond to these fractions that have denominators not divisible by P. The maximal ideal corresponds to all fractions that have enumerator divisible by P. And so this is generated, this ideal is generated by a single element P. And we have this, so these are all the ideals that appear in this ring. So these discrete valuation rings are very nice. They're generated, they're governed, the behavior of them is governed by a single element in the field of fraction. It determines everything. That's why discrete valuation rings are very simple, very nice to deal with. So we have this result. So we have this result here, that it's a classical result. Perhaps I'm tempted to say it's due to Serre. but perhaps it's older than that, but it appears in Serre's local algebra for the first time. It's kind of a strengthening of Krull's result. What we have to remember here is that this is a crucial assumption that R bar is Noetherian. And the integral closure in general may fail to be Noetherian. So now I want to talk about, I want to set up, I want to give the statement of my result. But before that, let me remind you about a basic definition from commutative algebra, namely I want to remind you of the concept of associated prime. So here is a definition. These associated primes will play a crucial role in what follows. So I have a ring, commutative ring R, and M is an R module. So a prime ideal P in R, so that's a prime ideal, is said to be associated if there exists an element associated prime of the module M, if there exists, so we didn't notation, this is how we denote it. If there exists a non-zero element in the module such that P is equal to the annihilator of this element. What is the annihilator? These are all elements in the ring R that annihilate when we multiply them by M, we get 0. So this is the definition of an associated prime. Well, let's look at examples. So what are the associated primes of, let's say, Z viewed as a Z module? Well, I mean, this is only one, it's 0, yeah? It's because A times B in Z equals 0 implies that one of them has to be 0. Well, if M cannot be 0, then the other element has to be 0. So this is the only case. This is the only associated prime. How about the associated prime of Z? Let's say Z modulo PZ. P is prime. Well, in this case, we get P. Yeah. And so it's a fairly simple computation. You can, let's say, pick 1. What is the annihilator of 1? So these are all elements in the ring that are divisible by P. When you multiply them by 1, that goes to 0. And that's the only thing that we have here. Okay. So I want to consider now the question of integral closure in the relative setting. What do I mean by this? Here is the relative setting. So I have A and B Noetherian domains. And I will assume that B is a finitely generated A-algebra. Meaning I need only finitely many elements in B to generate B as an A-algebra. Okay? So finitely generated A-algebra. And I'll define the integral closure of A in B, denoted by A bar, in the same fashion. So I'm looking at all elements in B that satisfy an integral relation of this form. Okay. So this is the relative setting. Instead of looking at an integral closure of A in its field of fractions, I'm looking at the integral closure of A at some extension algebra of A. So geometrically, this corresponds to the following situation. So you have morphism between algebraic varieties or schemes, locally affinite type. This locally affinite type translates to this condition that locally the ring of functions of Y is a finitely generated algebra over the ring of functions of A. So I mean, you can think of the local situation. And here we have the normalization, which corresponds to this spec of A bar. So it's an intermediate object. So I'm normalizing X in Y. So this is the point of view taken by Grothendieck, so who studied all these relative situations. And now the basic question is, can we have a theorem of the type of the type that I mentioned before due to Krull and Serre? Do we have such a description for A bar? It's a very basic question. So the main result of my first paper is the following theorem. So one of the following quotes. So the first possible case, there are two extreme cases. The integral closure is equal to B. Yeah. So B is integral over A. All elements in B are integral over A. So in this case, A bar is equal to B. That's one extreme case. The other extreme case is happens, for example, when B is just like a polynomial ring over A. Like all these elements that we are adding to A to generate B, they have no relation whatsoever. So this is one instance of what I'm going to put now here. But yeah, these are two extreme cases. It's the set of associated primes of B divided by A bar is equal to 0. No other associated primes. And this, what I described, happens in this case. So these are two extreme cases. And the third one, the kind of nice case, is the following statement: there exist unique and finitely many discrete valuation rings V1 to Vs in the field of fractions of A bar, such that A bar is equal to the intersection of these valuations with B. Well, this is the analog of the Krull-Serre result, but the difference here, the main difference here, is the finiteness of the valuations. So in the previous setting, when we considered the normalization in the field of fractions, there will be almost always the case that you will need infinitely many valuations. But this finiteness condition of B, B is a finitely generated algebra over A, gives us finiteness of these valuation rings. And they're also unique. So they're also unique. This is important. So there was one result of this type. I have to mention this due to Rees for a very special class of rings, A and B. Rees algebras of ideals of this flavor, and it was believed that this finiteness of the valuations was some phenomenon for these rings. But this result proves that no, it's a very, very general result. All you need to assume is that B is a finitely generated algebra over A to get this finiteness and uniqueness of these valuation rings. So I'm going to say a few words as a remark here, again, back to complex analysis. And then I will give a sketch of the proof. I will concentrate on what is really the main new ingredient here. And then I will give two applications of this result, if time permits. So I just want to remark here that, well, suppose that we are in this situation where, so we have y spec of B, x is spec of A, and suppose y over to x is birational. Algebraically, this means the field of fractions of A and B coincide. So, in fact, let's work over the complex numbers here. So it's and this A and B assume that complex analytic algebras. And I start with a meromorphic function on X. So here is my X. And the statement that this translation of this finiteness of these discrete valuation rings translates to the following statement, that there exist only finitely many curves here in X. There are finitely many curves in X, along which one needs to verify that this function g of x, so I will assume that also g of x is an element in B. So this is a holomorphic function on y, which is meromorphic function on x. And there only, the statement is that there are only finitely many curves in X, along which one needs to verify that g of x is locally bounded, meromorphic function, in order to conclude that g of x belongs to the normalization. So this is a translation of this statement in complex analysis. Only finitely many curves in X for a meromorphic function on X that's homomorphic on B. You need to check this local boundedness condition along only finitely many curves. Well, constricting, like saying what these curves look like, it's not that trivial. Okay, so what is the proof? I want to give a sketch of the proof. Now, one obstacle, here I want to point out one obstacle is that in general, the result is stated in such a great generality, which allows for A bar to be non-Noetherian. So here I say A bar may fail to be Noetherian. And you see, if you want to derive this result somehow from this result of Serre about the, or Krull, or whatever it is due to, if you want to derive it from this result, there the integral closure or normalization, it's assumed to be Noetherian. And then you get it as the intersection of the discrete valuation rings. Here, it may happen, there are examples where A bar may fail to be Noetherian. Nevertheless, we get the conclusion. So what is this key? I'm focused on the third part of the theorem, this key decomposition. I also call it valuation decomposition of the integral closure because it involves unique discrete valuation rings. So we can build this analogy with the decomposition in terms of associated primary decomposition for modules. We can have the same concept here for decomposition in terms of valuation rings for the integral closure. So what are these VIs? So these VIs are very special. So here I will look at the set of associated primes of this quotient. So I look at the quotient of B and A bar, and I look at the associated primes of this quotient viewed as an A bar module. A bar may not be Noetherian. So it turns out that if Q is an associated prime here, then A bar Q, denoted by QI is a DVR. And in fact, I'm sorry. In fact, yeah, it is the localization of A bar and QI is one of these VIs. So we'll show that. I mean, the main point here is to show that this set is finite. That this set is finite, that there are only finitely many associated primes. And then each of these valuations is simply the localization. And of course that the height of all these QIs is 1. And then each of these valuations is just the localization of A bar at a height 1 prime ideal. Okay, so how do we do this? Well, one needs to somehow show that this A bar, it may fail to be Noetherian, but it is generically Noetherian. So the first step here is to prove that there exists an element F in A bar such that A bar localized at F is Noetherian. So then the second step is to show that this set is finite, the set of associated primes. So this set is finite. Then we set each of these valuations is localization here, and then we get that A bar is contained in this intersection. So to get the other part, the opposite inclusion. So if B is an element in VI intersected B, then if you consider the ideal such that when you multiply B with an element in A bar, that this belongs to A bar, then it's not difficult to see that the radical of this ideal corresponds to some subset of intersection of associated primes. So this will be Qj, where Qj is an associated prime here. Okay. And from here one gets the opposite inclusion. So this is kind of the architecture of the proof, but I want to focus on one aspect of this work. So how do we get, so this is the crucial aspect, how do we get that this set of associated primes is finite? So, well, the first, so I want to comment on number 2. So the first part is to show that this is Noetherian, so that there exists F, such that this is Noetherian. This is, let's say, not that hard. And then if you pick an associated prime in this quotient, this key quotient, there are two scenarios. Either F belongs to Q, or F does not belong to Q. So if F belongs to Q, if F does not belong to Q, then Q is an associated prime of A bar localized at F, B localized at F, and A bar localized at F. This is fairly, it's an easy thing to verify. Now you see this A bar localized at F comes into play, which is Noetherian. So this is important. And if F belongs to Q, then the situation is handled by the Mori-Nagata theorem. So there is a classical machinery developed for this situation. I'm not going to talk about this. So I will focus on this case. So how do we prove what this, the main ingredient here is the following statement. So we reduce this finiteness, in this case, is reduced to the following proposition. Suppose A, B are Noetherian integral domains. B is a finitely generated A-algebra. And then the claim is that then the associated primes of this quotient is finite. You see, this quotient B divided by A, it may not be a finitely generated A module. It's yeah. So if it's a finitely generated A module, this is a classical, but that's the point. It's not a finitely generated A module in general. Nevertheless, this quotient is finite. So if there is one proof I would like you to get from today's talk, is the proof of this proposition. It can be, of course, it can be described in, can be included in a basic as an exercise in commutative algebra. So I'll give a sketch here, leaving the details, some like technical details, but the case to consider is when B is generated by one element over A. One can reduce quickly to this case. So there can be algebraic equations involved with this T, right? So if it's a polynomial, if B is a polynomial ring over A, this is very simple to handle. But in general, you can have plenty of like infinitely many, in fact, algebraic relations that are not algebraically dependent in an obvious way. So what you do in this case is you consider these modules. So A plus AT plus, I look only at polynomial expressions of this type up to T degree of T to the I. Okay, So this is a finite, AI is a finitely generated A module. And what I have is this chain. So you see, the problem with this chain is that yeah, it doesn't have to stabilize. If it stabilizes, then we're done pretty much. But it may not have to stabilize because, as I said, you can have new and new relations coming in arbitrary high degree. So here is what you do. It's a trick that somehow appears in a work of Hochster and Roberts in their generic freeness lemma. So you consider these quotients, this filtration. Okay, so there is a map between this quotient, it's multiplication by t. And I can look at the composite map from A1 divided by A0 to AN plus 1 divided by AN. Okay, and I can look at the kernels of this map. So I have the kernel of phi1 is contained in the kernel of phi2 is contained in the kernel of phi n. But notice that these kernels, they're all submodules of A1, A0. And A1 quotient with A0, it is a Noetherian module. Yeah, so it's finitely generated A module. So that chain must stabilize. So this chain stabilizes eventually. Or what I get is that for n large enough, AN divided by AN minus 1 is isomorphic to AN plus 1 divided by AN. So eventually, all these terms that appear in this infinite chain become isomorphic to each other. But from here, it's easy to see that if I look at now at this set of associative primes, then this is finite. Yeah, because you see there all these modules that appear in this infinite sequence, they're isomorphic. So this set of associated primes is finite. It's governed by this part and by this part. There are finitely many of those. And from here, one concludes that the set of associated primes is finite. So this is the proof of this key proposition. And I think I have 10 more minutes. So I want to talk about two applications of this valuation theorem. This is the last part. Two applications. So one of these applications is in singularity theory, is to singularity theory. I'm not going to state it here. I'm just going to visualize it briefly. I'm not going to, I'm sorry, I'm not going to give all the details because we don't have time, but the situation is the following. So you have a family, so this is some parameter space, and you have a family of singularities. Okay. So let's say this is some special singularity, the one that I'm underlying here. And I want to see all these nearby fibers, to this special singularity, how they behave. Okay, so I have some nearby fibers. And you want to do what you want to do. Maybe I should use a different color. I never used before a different color, but maybe now it's the time to use a different color. So you look at neighborhoods in the base space, and you shrink. You want to see as you get closer to closer. Let's say this is the origin. As you get closer to the origin, how these nearby fibers behave. So you want to construct an open neighborhood U of the origin, such that the nearby fibers of this special singularity, let's call this X, nearby fibers to X, have some property or share some property. So the way you construct this neighborhood is you shrink it and shrink it and shrink it and shrink it. But if you don't have, so the finiteness condition of these valuations, the finiteness condition of these valuations guarantees you that you have to do this finitely many times. Valuations tells you that you have to do it. You have to shrink this open neighborhood in the parameter space finitely many times. If you don't have the finiteness, you might end up just with the origin. So if you shrink this open neighborhood of the origin infinitely many times, in the limit you might just end up with the origin, so you cannot say anything about the nearby fibers. The finiteness condition guarantees you that there is a real neighborhood there of the origin that contains other points than the origin. And the other application that I want to talk in the next 6 minutes about is a variant of Zariski's main theorem. So this was application number 1. And now I want to talk about application number 2. So a variant of Zariski's main theorem. So remember the different versions of Zariski's main theorem that I described in the beginning of my talk. So here we looked at a relative situation. So I have spec of B, which is my Y. I have spec of A bar, which is my X bar. It's the normalization. And here I have spec of A, which is my X. Okay, so this is the situation. I write purposefully these specs on the top row to indicate the algebra behind the geometric picture. So now I can consider this morphism from Y to X bar, and I'll call it G. And I'll assume further that we're in a birational situation, well, slightly more general, that the fraction field of A bar is the same thing as the fraction field of B. Okay. Then here is the statement. It's a Zariski type, type result. If G is surjective, then Y is isomorphic to X bar. So remember, in the previous case, we had, in the absolute case, we had this G was assumed to be bijective and birational. If it's bijective and birational, then we have an isomorphism. In this case, just the surjectivity of G yields equality of y and x bar. Or here, the way we're going to interpret this is b is equal to a bar. How do we prove this? So here is a sketch. And with this, I'm going to conclude. So in the remaining 3 minutes, perhaps I'll be able to give the proof. So if Q is an associated prime, start with an associated prime here. Well, we know that A bar localized at Q is a DVR. This is part of the valuation theorem. It's one of the steps to prove the valuation theorem. But because Q is an associated prime, we know that A bar Q is not equal to B localized at the complement of Q in A bar in this multiplicative set. This is, so if Q is an associated prime, then Q belongs to the support of this quotient. So what do we have? AQ is a DVR. A bar Q is not equal to BQ. So there, but you see, for DVRs, there is nothing in between. So there are no proper rings that lie between the DVR and the field of fractions. So then the conclusion is that BQ must be equal, B localized at Q must be equal to the fraction field of B. And so that's a contradiction. So that contradicts the assumption that there exists a prime in BQ that contracts to Q. So you see, the assumption here is that of surjectivity. G is surjective. It means that in B, I have a prime that lies over A bar. When you localize, that property is preserved. So when you localize, this property means that there is a prime in BQ that contracts to A bar Q, but BQ is a field. So there are no primes there. So that contradiction with the surjectivity means that there are no, so therefore there are no elements here in this set. There are no associated primes, but we know no elements in this set. But we know that if a module, well, there's some important steps here that I'm skipping, but if you have a module with no associated primes, yeah, then that has to be 0 is equal to A bar. So this is a Zariski type result in this relative setting, which has some nice applications. Okay, thank you very much for your attention.
Okay, let's thank the speaker. We should, if you have any comments or questions, you simply can unmute yourself and simply talk.
Hi, it's Marin. First of all, Happy New Year. I have a question. Is the construction, so is this statement about the finitely many valuations explicit, or it just gives existence? So can you identify which?
Yes. So that's a very good question. Computationally, of course, it will be an involved problem. Just, you get the algebra and okay, what are the equations, or what are these valuations? but there is a very nice geometric interpretation of it. You need to assume that these algebras A and B are graded. If the algebras are graded, which corresponds to the projective situation, then there is a very nice interpretation of these valuations using classical result due to Chevalier. You can describe them in terms of localization at the generic points where certain fiber dimensions jump. Yeah, so there is a nice geometric interpretation, but you need an extra hypothesis for that. You need a compactness hypothesis for that. Without it, I don't think it's that easy to describe explicitly the valuations.
Okay, cool, thank
you. Some other questions or comments?
I have one remark. There was some geometric interpretation where these discrete variation rings were associated to curves. Shouldn't these be hypersurfaces?
Yeah, they're very good question. Thank you. So they are hypersurfaces. You have to check what happens at the level of the hypersurface, but in order to check on the level of the hypersurface, you need curves that are transverse to the components of these hypersurfaces. I hit some mathematics there. Yeah, the intuition is that it has to be exactly this. Associated primes need to correspond to generic points of some hypersurfaces, but what happens is that you need only some analytic arcs that are transverse to the components of certain hypersurfaces to check this boundedness condition.
I'm sorry, but I was disconnected for a while. Are there some other questions or no? If not, I want to make an announcement for the next Friday. Next Friday, this is the 14th of January. And for the fourth year, we celebrate the World Logic Day. And if you remember, a year ago, we had a very long seminar with 10 talks from our institute, the Institute of Philosophy, and the Faculty of Mathematics and Informatics of the University of Sofia. This year, probably we shall join also one more institute from the Academy, Information and Communication Technologies. And also we expect some important guests. I expect that the Minister of Education and Science will be, of course, the President of the Academy, the Director. We shall invite also the Brazilian ambassador, who was the main person to include the World Washington Day in the calendar of UNESCO. So the meeting starts in the morning and will be until the late afternoon. The program will be announced the next week, and we shall use Zoom again. So you're welcome to participate, to be in the meeting. The speakers already fixed, so you cannot be a speaker.
So no, I can just stop recording and you can switch to talking to each other in whatever languages on whatever topics you wish. And see signs of another meeting starting in using the same Zoom channel. So I'll stop recording now. Thank you for the talk, Antoni.